Yeah,
So,
perfect.
so this is, as Dr. Ankit was mentioning, this is your second lecture on this particular short-term course of quality control, material testing procedures, and lab practices. So, in this particular 1.5 hour discussion, we'll be seeing little bit of, or we'll be kind of getting a brief glimpse of what are the laboratory tests that we perform and how the quality control need to be done, right? So I'll be essentially talking about two different kind of tests. One is for determining the index properties of the soil, and the other will be like more kind of quantitative kind of test, like the compaction test, severe kind of test, right? So index properties, as this book's definition suggests, that it's a kind of a test to have the qualitative properties. So that's a very important part. Remember this thing, this the values that we'll be getting from this index property test, it's not good enough to represent the soil from quantification aspect, right? It will give you some kind of glimpse of what is the quality of soil, how good the soil will be, or, and in a sense, because these tests are very simple to perform, and it's easy to comprehend, but it's actually difficult to actually use this data for quantification, right? So people are doing this research for the past 6 7 decades, and they are, people are doing right now, they are performing this kind of test. The reason is that the soil is a very highly variable material, right? So most of the expression, or most of the equations that we get in soil mechanics, are kind of empirical in nature, and wherein our wherein our objective is to have this simple kind of test to talk about the most complex kind of phenomenon, right? So in index properties, we have this soil grain properties as well as soil aggregate properties. In soil grain properties, it's all about that how your size of the particles, how your shape of the particles, how your kind of arrangement of the particle, in a sense, kind of dictate the soil behavior. I'm against kind of emphasizing on this word qualitative behavior, right? And in case of soil aggregate property, what we'll be seeing is that how the kind of interconnection of the particle, right? So when I was talking about soil grain properties, I was kind of specifying to the individual particles, not much on the interactions of the particle, right? So when we'll be talking about soil aggregate properties, we'll be talking about this interaction stuff, right? How closer they are, right? So what is the impact of one particle to the other, right? So in that sense, soil aggregate properties are kind of different than your soil grain properties, right? So in this talk, I'll be kind of focusing much on this grain size distribution and on the Atterberg limit, right? Now, because shape of the particle itself is a quite complex phenomenon, and believe you me, right now there are very few labs, and especially in our country there are very few labs, and most of the studies are kind of analytical or kind of numerical in nature. So very few experimental lab to talk about the shape of the particle and have to have kind of some kind of influence on the shape of the shape of the particle on the mechanical behavior, right? But so in practice, we normally go for this grain size distribution. We talk about these Atterberg limits, relative densities, specific gravity. So these are the kind of properties that we normally use in practice, right? I'll be focusing much on this grain size distribution and Atterberg limits. So grain size distribution, in a sense, is kind of a fundamental physical property. What does that mean? Fundamental means that it will be unique to a particular soil, right? Now, if I take a let's say 500 gram of sample, wherever I perform this experiment, no matter let's say if I perform the experiment on Kashmir or Kanyakumari, you will have the same grain size distribution curve, right? That this statement is not kind of kind of a statement to be made for the other property, right? And that's for the reason that this grain size distribution curve makes so much of sense, right? So it doesn't depend on your environmental aspect, right? It's in a sense a fundamental, or if I have to use the word, intrinsic soil property. Now it reflects this, not only that this depositional aspect, transportation, but also this sedimentation mechanism. And that's where we actually use this sedimentary analysis also for understanding this grain size distribution curve, right? So for understanding this fundamental physical property, we will be performing, or we normally perform, two different kind of tests: the sieve analysis and sedimentary analysis. Sieve analysis are normally being performed for coarse grained material, and sedimentary normally being performed for the fine grained material. Now, in case of sieve analysis, we perform both the stuff, dry sieve and wet sieve. I'll start talking about this dry sieve first, and later I'll be just saying that why that wet sieve is required and how to perform that, right? So sieve, as now obviously all of us have done this sieve analysis, and we have seen this, that the sieves are square in these openings are square in shape, right? Now there is some kind of geometrical reason for that, right? That why it's like, why that this openings are square, why it is not like kind of other shape. Obviously one of the basic reason is what anyone can understand is, in a layman way, that this is quite easy to kind of fabricate, right? If it would have been other kind of shape, it would be difficult to perform, difficult to kind of arrange it, right? Now apart from that, there is one more reason to it. The physics is that its specific surface area, or in other words, that the probability of the particle to pass through this square shaped, right, square shaped sieve is higher than your circular or kind of elliptical, which are possible to make in the openings, right? So sieve number are being denoted by the size of opening of this, or the size of this squares, right? So let's say if I say that a 75 micron sieve, what I essentially mean that the opening of that sieve, or the size of that square, is 75 micron, right? So how to perform this the sieve analysis? First, we take some amount of soil, and wherever we see some kind of lumps, we kind of pulverize that, right? And then we kind of sieve it through this mechanical device, right? And we have this indicator for us that, like, if it is like, if the soil particles are greater than 75 micron, they are being termed as like coarse grained particles, and if they are less than 75 micron, they are termed as fine grained particles, right? Now so this is how we kind of define this coarse grain and fine grain. And in case of coarse grain, we also have this something called gravel size particles and something called sand particles, right? So, and this demarcation is by that 4.75 mm sieve, right? So while performing this sieve, we have kind of two different kind of fraction in a sense. So the particles which are higher than 4.75 millimeter, they will be tested by using different sieves, and the particles which are less than 4.75 mm, that will be tested in other kind of other arrangement of sieves, right? And the particles which are less than 75 micron, there will not be performing sieve analysis, will be performing hydrometer analysis. Why we'll be performing hydrometer analysis? What is the problem in performing sieve analysis? Because these particles which are actually less than 75 micron, they are very small in size, and this particle, first of all, they don't look like this angular or spherical kind of particles. They are quite charged particles. They actually kind of flock together with each other, right? So when the particles are flocked together with each other, the diameter of the entire arrangement is actually quite high, right? So probably the individual particle can slide through a particular sieve, right? But as these particles are charged together and they are attached to each other, they make a large kind of shape, right? And this particular size, or this particular size of this flock, will not pass through that particular sieve. So there will be kind of a misnomer, right? So but for avoiding this misrepresentation, there is no sieve analysis being performed beyond this 75 micron sieve, right? So the reason is that this charged this stuff, right? So but remember this thing, that below 75 micron, right, the particle doesn't look like to be this spherical or some kind of angular kind of stuff. They are platy in nature, and they have charge in their bodies on the surfaces, right? They attract the other particles. The particles come closer to each other, and once the particle comes closer to each other, they kind of for this kind of they start to make this flock, right? And this flock will not pass through that particular sieve, right? And that's the reason that we don't perform any sieve analysis below 75 micron. So what we do is, so above 75 micron particles, we perform this sieve analysis, and we have a kind of demarcation over here, as we have mentioned that there is this 4.75 mm, right? So we have this gravel fraction above 4.75 mm and sand fraction below this 4.75 mm, right? So when we perform this test, we use different sieves for the gravel fractions and for the sand fractions, right? So these are the sieves that we use for the gravel fraction, and these are the sieves that we use for sand fractions. So the way we perform the test, so for the, when we perform the gravel fraction, so these are the sieve sizes that we use: 80 millimeter, 40 millimeter, 20, 10, and 4.75 mm, right? And we kind of put it on this mechanical shaker. We shake it for some amount of time, and after that, whatever it is being retained on each of the sieves, that are actually weighed, right? So let's say W2 is the weight of the particles, right, that is retained on 40 millimeter sieve, right? W3 is the weight of the particle that is retained on 20 millimeter sieves. So we kind of weigh this amount of particles that are being retained on each of these sieves, right? And then we calculate something called percent retained on each of the sieve, right? What is the percent retained on first sieve, second sieve, that we calculate. And our objective is to kind of obtain that how much percent actually is being fined for or finer from a particular sieve, right? So what we actually calculate is that what is the cumulative percentage of retained for on each of the sieve, right? So let's say if I have to say that what is the cumulative percentage of retain on this particular sieve, what I'll do is I will add up the amount of the soil that is being kind of collected on all these sieves, right? So once that is being added up, right? So what I can understand is that whatever the sample that I have taken, so if that is 100%, and the kind of percentage of particle or percentage of soil that is being retained up to this sieve is, let's say, 30%. That means like 70% actually is passed through this sieve, right? So 70% is the retain is the percent finer for this particular sieve number, right? So that's how we actually performed cumulative percentage of retained, wherein we add of, let's say, if I have to get what is the percentage retained on fourth sieve, I'll add up to all this percentage retained, right? And then I will be kind of subtract or this, I'll be getting this percent finer by subtracting this from this 100%, right? So that's how we'll be getting this percent finer for a particular sieve size, right? Which is like this 100 minus cumulative percent retained. So once this is being done, so we are in a position to understand that that how much percentage of finer is there for each of the sieve, right? So for 80 millimeter, how much is the percent finer? For 40 millimeter, how much is the percent finer? End of the day, our objective is to find a grain size distribution curve, right? So grain size distribution curve, as I was mentioning, that it is a kind of a fundamental property of the soil, right? Very few properties in soil are fundamental, right? Grain size distribution is is one of them, right? Now in to plot this grain size distribution, we need two stuff, right? In x-axis and in y-axis, we need two stuff. In we need the diameter of the particle, and for each of this diameter particle we need this percent finer, right? Remember this thing, while we perform this entire analysis, we have some kind of assumptions, right? How valid these assumptions are, that is debatable, right? Now, as I was mentioning, the shape or this your sieve openings are square in nature. There is some argument to it, and people are seeing this thing, that is there any other better way of representing these sieves, right? So whether is there a need of having a kind of different shape of sieves, right? It is not yet being solved. People are kind of debating on it. But for this particular, or in the code that people came out in the code, what people have suggested is that you assume that the particles are in a sense spherical in nature. So whatever the diameter that you will be talking will actually be representing their representation of the representative diameter, right? So particle may be some kind of this kind of shaped, right? We will be assuming the particle to be a spherical, right? And assuming this particle to be spherical, what we are doing is we are kind of reporting this diameter over here, right? So what we need is diameter of particle. So when I say diameter of particle, you need to keep it in mind that it's a kind of representative diameter of the that particular assumption. This is your actual this particle which we are kind of assuming it to be spherical, right? Is it a good idea? Again, a debatable stuff, right? And while we do it, there is some kind of geometrical stuff that is being involved, right? Like the volume of each of this particle is being assumed to be the same as the volume of this sphere, right? Obviously the surface area is not taken to be the same, the volume is taken to be the same. Again, that's again a part of this debate, right? Now but we necessarily talk about the diameter of the spherical particle, right? And for corresponding to each of this diameter, we will be kind of, our target is to get this percent finer. And how we'll be getting this percent finer? Through this particular formula, right? So let's say W4, which for this particular gravel size distribution, it will be representing like 10 millimeter, right? So what we'll be seeing is 10 millimeter is kind of retaining this amount of soil. So this amount of soil, which is being kind of boxed by this blue line, is kind of passed through this particular sieve, right? So this percent, this is kind of the percent finer that will be placed on this y-axis, right? And we'll be getting a data out of it. So that's our job from this grain size distribution as far as these coarse grained particles are concerned, right? Now, in the first slide, I was also talking about not only about the dry sieve analysis, I was also talking about wet sieve analysis. Now, first of all, whether the wet sieve analysis is required, the answer is yes, it's required if more than 5 to 10% or more than 10% particles actually pass through this 75 micron, right? So you can take a call